Thanks a lot, Wuhan, for the introduction. Yeah, so today is the last lecture in my lecture series, and so today we're going to put it all together and conclude the proof of Kolyvagin's theorem. But before I do that, I want to go back to the kind of aside I finished off yesterday, which was so yesterday we constructed these classes. This collection of Kolyvagin derivative classes, and we show their nice properties. Okay, and then here I mentioned that Kolyvagin in 1991 conjectured that this system is always non-zero. Okay, but to this literally be Kolyvagin's conjecture, really one needs to work with an enlargement of this C infinity. Okay, because the C infinity we built in yesterday's lecture, which was all consisting of classes modulo P. Okay, and this system is known to be non-zero only when certain Tamagawa factors are trivial. They have no p-par. Okay, so Kolyvagin conjecture that this system is always non-trivial, but when you enlarge it to include classes mod p to the n for possibly higher powers of p. Okay, so this is a little addition that I should have added when I mentioned this yesterday, and actually in the version of the notes uploaded in the website, it's corrected with this addition. Okay, but again, in any case, this was an aside. All right, so now, as I said, let's put it all together. Okay, so first let me begin with a little lemma. Okay, last time we introduced the notion of a Kolyvagin prime. And something we saw is that any prime L in what we call Elsa P was one of such primes. Okay, and I'll remind you of the definition as we go through the proof. Okay, and as we always do, let's write. So these primes are in particular inert in K. So I write it like this as usual. And now the claim is that when we look at the singular quotient locally at this lambda, and I look at the plus and minus eigenspaces and their complex conjugation, each of them are one-dimensional. Okay, so this is a little calculation, but it will allow us to remind ourselves of some of these things that we saw yesterday. Okay, so by definition, well, we checked that being a prime in Elsa P would imply that this Frobenius element attached to the prime L was conjugate to tau, okay, where tau is complex conjugation. Okay, and we also saw that, and L is also inert in K. Okay, therefore we can now compute the Frobenius of the prime lambda. And then by the way Frobeni work, this is going to be the square of the Frobenius of the rational prime L. Okay, so we're going to get something conjugate to tau square, but that's of course identity. So this is telling us that the prime lambda splits completely up to this extension. Okay, so we get lambda splits completely. Yes, so I'm using the same setup we had yesterday when we started constructing Kolyvagin's classes. Okay, so imagine a quadratic field satisfying the Heegner hypothesis, etc. Okay, so lambda splits completely in this extension. So in particular, if we complete K at lambda, we're going to get the same as the completion of this guy at any prime of lambda, but this contains all the p torsion. So what this is telling us is that the p torsion of E, all the p torsion, is actually contained this completion of K at lambda. And therefore, the decomposition group at lambda acts trivially on the P torsion. Okay, so JK lambda acts on the P torsion trivially. Okay, but now by inflation restriction, okay, this singular quotient that we want to compute is actually the same as H1 of inertia on the fixed point. P now fixed by GK lambda modulo E sub lambda, where E sub lambda is the inertia subgroup. Okay, but we just said that GK lambda is acting trivially, therefore, so that's inertia. So this H1 just becomes ohms, G equivariant ohms. Okay, and this is just generated by Frobenius, so it's Frobenius equivariant ohms. Okay, so this is isomorphic to ohms. Okay, these ohms are all Frobenius equivariant from E lambda to the P torsion. Okay, but now this prime L is not P, so these ohms will naturally factor through tame inertia. And we know very well the structure of tame inertia as we saw in Somnath's first lecture. So this actually is going to be isomorphic to ohms as Galois modules from UP to EP. Okay, now we're done because we just need to take plus and minus eigenspaces. These isomorphisms are all tau equivariant. So we're going to get okay, so we get H1 singular K lambda EP plus minus is going to be the ohms now being a ohm which is in the plus eigenspace under tau means that it preserves the tau eigenspaces, and being in the minus will mean that it reverses them. Okay, but we know that the action of complex conjugation is odd on mu p, so that's going to be isomorphic to EP minus plus respectively, and now this is what we want. Okay, so that's a little lemma, which now we can use to conclude. Sorry, I'm skipping up. Oh. Missing a page. Okay. All right. So now we're finally ready to prove. Okay, so to what we call theorem A prime, which I'll restate. So, oh, sorry. I left one of the pages back and I was missing that. Okay. Okay, so call it back in. Okay, so we state as follows. So we were assuming that the point y sub k is not non-torsion. And we picked what we call a good prime. Okay, so let me satisfying these three properties. Odd, the Galois group of QI join the P torsion is FL GL to FP. And y sub k is P indivisible. And then the conclusion was that the mod P Selmer group is actually spanned by the Kummer image of this y sub k. Okay, where usual delta is the Kummer map. Okay. In fact, we're going to see in the proof that all we're going to use really is this part. Okay, the fact that yk is non-torsion will not be used in that proof. Okay, but I wrote in this way to connect it to the theorem of Kolyvagin we stated in the first theorem. Okay, because as soon as yk is non-torsion, then for all finding many primes p, we're going to have this third condition. Okay, so okay, so as we already explained, the proof of this boils down to bounding the size of this Selmer, because the assumption that yk is P indivisible is telling us that the Selmer group is at least one-dimensional. And now we want to conclude that it's no larger than that. Okay, so let's start the proof by doing the following reduction. Okay, so suppose we can find an integer n in this set we introduced yesterday, square free products of Kolyvagin primes. Okay, so this is just a product of t distinct Kolyvagin primes, so primes in this set LE, for which the following three conditions hold. Okay, so first, that when we look at the Selmer group and we impose triviality at all these primes, we get something trivial. Okay, so here we are taking S to be, okay, so these are all primes in this, these are primes in Earth in particular. So following the notations we've been using throughout, I'm just writing Li okay as lambda I. Okay. So suppose we have this. Second, that the point y sub k that we are assuming to be globally P indivisible, it remains P indivisible when we localize at each of these lambda i's. Okay, so this is P indivisible in these local fields, and that's the case for all I from 1 through t. And third, that now we have this class CL1, the Kolyvagin class of that conductor. So this is Kolyvagin derivative class. The derived class. Okay, and so it's a global homology class, but the condition C itself is that when we look at the restriction to all the other primes, lambda i's, these are also non-zero. Okay, so this is as classes in H1, K lambda I, EP, for all I starting at 2 now. Okay, so let's quickly see that if we can find an n satisfying A, B, and C, then theorem A prime follows. Okay, so then, okay, so suppose this. So then we get the following. Okay, so part A, combined with what we already saw in lecture 2. Okay, so lecture 2 was telling us that whenever we can bound the strict Selmer group, we can then compute the Selmer group we care about in terms of the co-kernel of some residue map. Okay, so we know that then the size of the Selmer group is the same as the size of this co-kernel. Okay, and the map here is this partial S, which is the sum of the corresponding residues. Okay. So that we saw in lecture 2. So now, if we take tau eigenspaces, and so taking tau eigenspaces, we get that the size of the, well, this size of this is going to be the size of the corresponding co-kernel. Okay, but now this partial S plus minus takes values in this in the corresponding plus and minus eigenspace of this singular quotient that we just proved is one-dimensional. Okay, and so now let's bound this one eigenspace at a time. Okay, so let's look first at the minus epsilon eigenspace. Okay, and as always, here epsilon is the opposite to the sign in the functional equation. As it's always been in these lectures, epsilon is such that LES is minus epsilon LE to minus S. Okay, so let's see what we can say about this eigenspace. Okay, so the second condition is now telling us by the work we did yesterday that the classes CLJ, okay, so this implies okay, actually was that proposition that took us the longest to prove, proposition 5. Okay, so this condition B will imply that when we look at the residue of the class CLJ, okay, we're gonna get 0 as long as I is different from J, and we're gonna get something non-zero when I is equal to J. Okay, so and the fact that we get non-zero when I is equal to J is what's guaranteed by this plus proposition 5. Okay, so I'm gonna write in this way. This is a non-zero multiple of Kronecker delta. Okay, when I view this, okay, so these are classes in the singular quotient for lambda I, EP, Okay, but remember these CLs belong to a specific eigenspace. In fact, to the minus epsilon eigenspace. Okay, so this thing is the same as minus epsilon CLJ, but now we land in the minus epsilon eigenspace, and this we just prove this FP. Okay, so when I identify this with FP, is the sense in which I'm writing this equality. Okay, so as I said, this is Kronecker delta. Okay, but now this and tau is complex conjugation indeed. Yes. So, but now this makes it transparent that these T different classes, CL1 through CLT, they are linearly independent. So the image of this partial S minus epsilon is at least T-dimensional. Okay, so this implies that the dimension over FP of the image of partial S minus epsilon is at least T-dimensional. But the target is T-dimensional, right? Because each of these guys are one-dimensional, and we have T of them. Okay, so this tells us that the map is surjective. Partial minus epsilon is surjective. And therefore, by this equality, let me call it star, we get that the minus epsilon eigenspace of Selmer is trivial. Okay. Any questions so far? Okay. So it remains to see, let's look now at the epsilon eigenspace. Okay. Now we look at the epsilon eigenspace. Okay, now we're going to use property C, we haven't used yet. Okay, so C is telling us now by, again, the work we did yesterday, that the residue at lambda I of now we look at the collivating classes indexed by two different primes. Okay, so we're going to look at L1, Lj, and so J is going to run from 2 to T, okay, because we need to take different primes. And again, we're going to get something which is a non-zero multiple of Kronecker delta. Okay, is 0 if I is not J, and 1 otherwise. Okay, again, as classes in the singular quotient for lambda I. And now we saw yesterday that when we add two primes, these classes are in the epsilon eigenspace. So this is now the same as epsilon component of the residue map. So now we are landing in the epsilon eigenspace, which is also one-dimensional, and this is now holding for all. Okay, this is good. This is for all I and J between 1 and T. Okay, but so now we get T minus 1 linearly independent elements in the image. And therefore, the target is again T-dimensional. So the co-kernel is at most one-dimensional. And therefore, by again this equality star, we get the dimension of the epsilon eigenspace of Selmer is at most one-dimensional. Okay. But we already know an element in the epsilon eigenspace of Selmer, namely the Kummer image of y sub k, and therefore that must be everything. Okay, so y sub k not in p y k, as we're assuming, implies delta yk is non-zero in here, and in fact, it's in the epsilon eigenspace. So we get okay. So so the opposite of this is if we can find. So now we have reduced the problem to finding an n for which A, B, and C hold. Okay, and it's at this point where we're going to have to use a clever use of Cherepov's density theorem. Okay. Okay, so the upshot of this is to conclude everything. It remains to find an n in this n sub p for which these A, B, and C hold. Okay. So this is always the part in Kolyvagin's arguments that is more of an art than a science, because in every application, one will need to find the right use of Kolyvagin's theorem, to choose the right primes for the application in at hand. And every case, even though they are all kind of similar, requires fine tuning for the application we are working with. All right, so okay, so in the remaining of today's lecture, so I have like an hour left. Actually, we'll be devoted to this part. Okay, finding such an n for which we have A, B, and C. Okay, so maybe this is a good point to ask if there are any questions so far.
Any questions from the audience?
So it's like a complex conjugation, somehow quite crucial.
Yes, in this argument of Kolyvagin is quite crucial, but just this is an artifact of the way we define Kolyvagin primes. We define Kolyvagin primes to be those that are conjugate to tau in a certain Galois group. But as in the usual, for example, in the context of cyclotomic Euler systems, as we saw in Chanho's lectures yesterday, and in Rubin's book or Mason Rubin statement, one actually chooses primes, chooses kind of the corresponding Kolyvagin primes to be those that are conjugate to an element tau on which one requires a certain action on the module one is working with. And that plays the role of complex conjugation in the setting of Heegner points. Okay, so in other situations, one fixes a tau for which one knows something about the action of that element. Let's call it sigma. So one fixes a sigma for which one knows that essentially that the coinvariants of that element are rank 1. And then the Kolyvagin primes one works with are chosen to be conjugate to that sigma. And that actually gives, yeah, that's actually more, it's more flexible in settings like the cyclotomic.
Can you say a little bit how the sign in the functional equation comes into play, like regarding the Kolyvagin classes?
Yeah, so this we saw yesterday. I still have it here. Yeah, so each of these classes, Tian, live in one eigenspace under complex conjugation. Okay, oh. And in fact, every time we add a prime to the conductor, we swap the eigenspace. Okay, so the classic one is in the epsilon. When we add a prime, it's in the minus epsilon. When we have two primes, it goes back to the epsilon, etc.
Oh, thank you.
Yeah.
Any other questions? Here, some echo, but
Okay, so
okay, I think
maybe
we can move on. Yeah.
Yeah, I'll continue. So, all right. So now, yeah, we'll spend the remaining of today's lecture doing this. So let me begin with another lemma. Okay, so I'm going to use this notation in all what follows. So I'm going to denote by L the extension obtained by joining to K the coordinates of the P torsion. And then, so this is obviously a Galois extension of K, and the Galois group is going to be isomorphic to okay, so this is this calligraphic G will denote the Galois group. And because of our assumption on P, this is isomorphic to GL2FP. Okay. And let's pick C, a subgroup of H1 K EP, which is it's a finite subgroup and is tau stable. Okay, so a finite tau stable subgroup. Then we can find an extension of this L, a larger extension, with the following property. Okay, so then, and clearly this extension will be unique. Okay, so there exists L sub C over L, a finite Galois extension, for which C, this given subspace of homology, now can be thought of very concretely. Okay, so working with this homology, sometimes it's good to have an explicit way of working with elements in that. Okay, so this is going to be isomorphic to the G equivariant homes between the Galois group of this extension. Okay, so this Galois group certainly has a G module structure where calligraphic G acts by conjugation, and then so does the P torsion. Okay, so we have this isomorphism. And which is an isomorphism of Galois K over Q module. As okay, and the isomorphism is quite natural, so the proof is essentially just going to tell us what it is. So proof. Okay, so this just follows from the fact that the restriction map to this L. Okay, so this restriction map goes from H1 KEP to this larger extension L. Okay, and it lands in the calligraphic G fixed part. Okay, but now in L, we have adjoined all the coordinates of the P torsion. Okay, so the absolute Galois group of L is obviously acting trivially on EP. Okay, so this just becomes G equivariant homes from the absolute Galois group to EP. Okay, so this is easily seen to be an isomorphism. So let me tell you why very briefly. Okay, since, okay, so again, there is an inflation restriction exact sequence that allows us to compute both the kernel and co-kernel here. Okay, so the kernel, this is nothing but H1 G EP. Okay, and I will have to take the fixed parts by GL, but L is acting trivially, so it's the same. Okay, and now this is the same as H1. The group G is GL to FP, and so this H1 is the same as the group homology of GL to FP, acting naturally on FP squared. Okay, and because P is odd, it's a standard fact that this H1 is trivial. Okay, so this uses the P is odd. Okay, and similarly, the co-kernel is going to inject into some H2 GEP. But again, by the same reasoning, this is the same as GL to H1, sorry, H2 now, of GL to FP, FP squared. And because P is odd, this is also 0. Okay, so this map is an isomorphism, and now you can. It's not surprising that if you fix a subgroup of this, it will now define. So a subgroup here will correspond to a subspace of homes here, and the Galois extension that you need to take will just be the one that is cut out by all the homes that you get on the right hand side. Okay, so once you have this isomorphism, the lemma follows quite readily. Okay, but it's going to be quite useful, and so we're going to apply this lemma by taking C to be the mod P Selmer group. Okay, so then we will be able to interchangeably think of elements in Selmer as homes from a certain Galois group. Okay, so let's do that now. Okay, so now we take C to be the P Selmer group. Okay, and let me write the following diagram that we'll be working with. Okay, so I'm going to call M this extension L sub C coming from the lemma. Okay, so I don't need to write L sub cell. This is L sub C for this particular C. Then we have this L that we introduced in the previous page. Okay, I joined the P torsion. Then we have the field K. And then maybe, okay, I'll come back to this diagram later and complete it. Maybe for now, I don't want to put more things in here other than the Galois groups. Okay, so we have, this group is what we call G. And this is, I'm going to call this group H. Okay, so H is the Galois group. M over L. All right, so by lemma 2, let me now restate it with this notation. Okay, so by lemma 2, we have that the P Selmer group is now the same as G equivalent homes from the Galois group, which is now H, to the P torsion. And this is a scalar modulus. Okay. Okay, so now another way of writing this isomorphism is as follows. Okay, so we're saying that having an element in Selmer is the same as having a home from H to the P torsion. So another way of writing this is as saying that we have a way of pairing elements in Selmer with elements in this group to produce elements in the P torsion. Okay, so this interpretation will be convenient. Okay, so a way of saying this is that we have a non-degenerate pairing between those two. Okay, so I'll denote by bracket. Okay, so here I'm using the same notation that Gross uses in his beautiful account on Coulibagin's work. Okay, so okay, and this map, it's coming from this this restriction map that we saw in the proof. Okay, so we can write it down precisely what this pairing is. Okay, so all it does is it's taking an element in Selmer and in this group, and we just restrict the cocycle to S. Sorry, we restrict the this homology class to L, so it becomes a home that we can evaluate at G. And when we do that, we get an element in the P. Okay, so that's another way of writing the same thing, but also we get the following. Okay, so for any prime, for any class in Selmer, and any prime lambda that doesn't divide NP, so prime of lambda, prime of K, I mean, that splits completely in L. Okay, so we just checked in lemma 1 that any prime in L sub P will have such property. Okay, so we're gonna be using that. Okay, so when it says lambda, we have the following way of checking local triviality of homology classes. Okay, so we have this global class is going to be trivial locally at lambda. Okay, so this is as an element in H1 K lambda EP. If and only if, in terms of this pairing that we just introduced, is the same as pairing S against this Frobenius element. Okay, and this is for some. Maybe I can write here. For some equivalently any lambda double prime dividing lambda in M. Okay. So this is going to be useful for us when, as you can imagine, when we want to check this type of conditions, okay, C and D, because now it's phrased in a condition in terms of Frobenius element, so it's something for which Chebotarev is likely to have. Okay, so we're here. Okay, so now I can go back to this diagram and add one more piece of notation that we're going to be needing. Okay, so sitting inside this M, that remember, one way of thinking of this M is the smallest extension of L that trivializes this Selmer group. Okay, so this Selmer group consists of homology classes. So we can always, for each of these classes, we can always take an extension of K that will make this homology class, which corresponds to a certain extension. It will split that extension. And this M is the smallest one on which we can simultaneously split all these Selmer classes. Okay, but sitting inside here, we can look at the one that splits the Kummer image of y sub k, okay, which is the same as looking at L and adjoining a pth root of y sub k. Okay, because of the explicit way of writing down the connecting homomorphism in the Kummer map. Okay, so we have this intermediate field. And this Galois group here, you can easily see what it's going to be. Okay, so it's going to be isomorphic to the p torsion. Okay, because I don't write, so it's a real argument to check this, but it's quite natural because any two pth roots that you take of y sub k will differ by an element in the p torsion, and the p torsion will act transitively on all these pth roots. Okay, so it's quite natural that the Galois group becomes isomorphic to this. And then this group, this Galois extension above, I'll denote by I. The notation for this Galois group. Okay, and I introduce this because it's going to appear in our next lemma. And after this, we can start checking A, B, and C one by one. Okay, so third lemma. So let's take a class S, which is a Selmer class in a fixed eigenspace. And let's suppose that under this pairing that we just introduced, it pairs to 0 against all the elements H in H plus minus I plus. Okay, so let's go back to this diagram. Okay, so both this H and this I will have an action of tau under, again, by conjugation. Okay, so it will split into plus and minus eigenspaces, and here I'm just taking the plus eigenspace. Okay, and it's immediate to see that this condition is actually equivalent to requiring the same vanishing, but now for all H in H plus. And that's just because okay, you can immediately check that the fact that this is a proper subgroup because we have this non-trivial quotient, and the restriction of L of S is group home. Okay, so we could alternatively write it like that, but we're going to be using the fact that it suffices to check it on these elements. Okay, that's going to be actually crucial for the argument. Okay, so suppose we have this vanishing on all these elements, then the class is forced to be 0. Okay, so let's see why. Okay, so for this, it suffices to show that now we're going to think of this S as a home on H. Okay, so it suffices to check that the image of H under S is trivial. Okay, so enough to check. S of H is 0. Okay, but we have assumed that this class is in a tau eigenspace, so the restriction will be still in a tau eigenspace. Okay, so the restriction of this class is going to be this home plus and minus. And again, we just use what it means to be in the plus and minus eigenspace under tau. So it's going to map okay, so if it is in the plus eigenspace, it's going to preserve the eigenspaces. Okay, so it's going to take H plus to EP plus and it's going to take H minus to EP minus. And if it is in the minus eigenspace, then it will swap the eigenspaces. Okay, so it will take then H plus to H minus to EP minus, and it will take H minus to EP plus. Okay, so we get this. And it's going to do that G equivariantly, of course. Okay, so G equivariantly. Okay, so now if we assume that S is vanishing on all of H plus, okay, so thus, if S of H plus is 0, then the image of H is the same as the image of H minus. Okay, so it's this guy. Okay, so we get this will imply that SA, the image of S, is going to be contained in EP minus plus, and because it's the image of a G equivariant home, it's going to be a G invariant subspace, and it's a proper one because it's contained in the plus or minus eigenspace. Okay, so this is a proper G invariant subspace of EP. Okay, but our assumption on P, the big image hypothesis, in particular implies that EP is irreducible as a Galois module, as a G module. Okay, so this implies that this SH has to be 0.
Francesc, there's a question in the chat box.
Yes, I saw that. Thank you.
Yeah.
The question is, can you once explain the term G equivalently? Yeah. So this just means that it's a homomorphism that preserves the G action. Okay, so G is acting on both terms, and we just want that phi of G acting on H should be the same as G acting on the image. It's just this condition. Okay, so that's what we mean by being G equivalent. Okay. Any other questions? All right, so now we are ready to check conditions A, B, and C. Okay, which I'll recall, probably by now everyone has forgotten. Okay, so let's prove condition A. Oops, I want to do this nice square here. Okay, which I remind you what it was saying is that we can find an N for which this Selmer group where we restrict the condition at the places in S, okay, where S are the lambda 1, lambda t corresponding to these guys. This is trivial. Okay, so actually ensuring this triviality is not that difficult. What is difficult is to make sure that the choice that we make here actually works in checking B and C as well. That's a tricky part. Okay, so let's list the elements in this complement, H plus minus I plus, as follows. I'm going to call them gamma 1, gamma t. And they are in the plus eigenspace. So using the fact that P is odd, one immediately checks that any element in the plus eigenspace can be written as follows. Okay, so this gamma I can be written as tau hi squared with hi in H. Okay, so this uses P is odd. And finally, once we've done this writing, pick primes Li away from N PMP such that this Frobenius for this extension is conjugate to tau hi. Maybe it is important, so let me put it, let me give it a central place here. So tau hi, and this is for I between 1 and t. Okay, that the fact that such primes exist, and in fact a positive proportion of them is of course ensured by Chebotarev's density theorem. Okay, so okay, so let's check that this actually will do the job. Okay, so the first thing we're going to check is that, well, we need to check that these primes are Kolyvagin primes to begin with. Okay, so let's check that. Okay, so for that, the first thing we need to see is, well, let's look at this Frobenius element. Now, so we're going to use now a number of times the different the behavior of Frobeni under different natural operations. Okay, so we know about this element by our choice, and that will be related to the 1 over L by via this relation. Okay, but now that's the same as taking tau hi restricted to L. And now if I go back to the diagram, okay, so this hi is an element in H, and H is fixing L. Okay, so when I restrict this to L, I'm left with tau. Okay, and we saw yesterday that any prime Li with this condition on the conjugacy class over L, which is K adjoint the P torsion, if that's conjugate to tau, the prime L belongs to L sub P. Okay, so it implies. Okay, so this we saw in lecture 3 that Li is in here. Okay, so that's a good start. Now we are here. Okay, so now let's check this vanishing. Okay, so well, now we know that these primes are in LE. In particular, they are inert. So let's do the usual writing. So write Li okay, yes, lambda I, and we put S to be the set of all these lambda i's. Okay, so now we want to check this triviality, this vanishing. So let's pick an arbitrary class there. Take S, a class here. And of course, we want to show that it vanishes. Okay, but the last lemma we showed is telling us that, well, so what we can do first is we take this class, we can project to the plus and minus eigenspaces, and to check that it's trivial, it requires to check that each of the tau components are trivial. And for each of these tau components, we just need to check triviality on these elements. Okay, so by lemma 3, it will suffice that we have S plus pair against H equal to 0 for all H in H plus minus I plus. Okay, and here by S plus minus, I'm denoting the image in the plus minus. Which of course sits inside the plus minus of the usual sum. Okay, but now, okay, so this we need to check for all the elements here, but we have listed the elements like so. So that's the same as saying that we want S plus minus against gamma I to be 0 for all I. Okay, and now you can do a little calculation. This one I'm not going to do. We're going to do the ones later, but you can check that this gamma I, by the way we've arranged this Frobenius element, this is the same as pairing S plus minus against this Frobenius element, the 1 for L over L of lambda I double prime. Okay, for all I, where this lambda double prime is any prime dividing lambda I in M. Okay, so here you just use the choice of Li. Okay, but now we just noted over here that this vanishing is actually equivalent to this class vanishing trivially at the prime lambda. Okay, so as we noted already, this is the same as S plus minus sub lambda being lambda I being equal to 0 for all I. But this is now guaranteed because our class is in this S strict Selmer group. Okay, and S is just the collection of its lambda i's. Okay, so this is checked because S is in this H1FS. Okay. Okay, so this checks condition A. Okay, so A holds. Okay, which, as you saw, it was not that difficult. We just, once we make the right choice of these LIs, the lemma gives it quite directly. Okay, but as I said, the difficulty is in having A and B and C all simultaneously. Okay, so any questions before I move on to now checking B?
Questions?
Okay, so
Yeah, I think we can move on.
yes, good. So let's now check B. Okay, which this was now a local pin divisibility of the Heegner class. Y sub k should be not divisible on k lambda I for all I. Okay, so this will be now a computation of for any I again. Okay, so for any I, if we pick a lambda, let's call it lambda I prime, dividing lambda I in L, let's look at this. Okay, so we're going to look at this extension we had before, okay, where we adjoin the coordinates of a pith root of y sub k. And so the way this is going to follow, the way we're going to be able to guarantee this pin divisibility will be by checking that the prime lambda I in here doesn't split completely in this extension. Okay, so it's easy to see that this pin divisibility boils down to this prime lambda I not being totally split in this extension. Okay, so for that we need to check that the corresponding Frobenius is non-trivial, and so we need to look at the 1/k, but the calculation the way it's going to go is first we're going to compute it over L and then deduce the result over K. Okay, so let's look at this Frobenius element. Okay, so again, now the familiar process. So this is the same as the 1/m, but restricted to this smallest extension. Okay, so that's one way of computing the thing on the left. Okay, and we do that because we have prescribed what is the Frobenius relative to the big phi m in our choice of Li. Okay, and we know that the prime lambda I will split completely in L. Okay, so this is the same conjugate to m/k lambda I restricted to the same thing. Okay, so that uses the fact that lambda I is split completely. In L/k. Okay, typically there would be an exponent corresponding to the inertial degree. Okay, and then this lambda I is inert. Okay, so now relative to Q, we're going to get the square okay, so this is because Li is inert in K/Q. Okay, but now by definition, we have chosen this, we've made this choice. Okay, so this is the same by definition as tau hi square restricted to this guy, to this field. Okay, but this tau hi square is gamma I. This is gamma I restricted to this. And this is non-trivial by the way we've chosen gamma I. Okay, so these gamma I are elements which are not in I. And the elements in I are precisely the ones that fix this extension. Okay, so this is not the identity, since this gamma I is not in I. Okay, but that already gives us what we want for B. Okay, because now this implies that this lambda I prime doesn't split completely. The square. Can you want to explain the square in the third last step? Oh yeah, so yeah, the square is just because, so when you're gonna go from relate these two Frobeni I, this one down here will be a power of this one, and the power that will occur will be the degree of the residue fields. And because lambda is inert, this is going to be FL squared, whereas this is FL. So these two, it just means the degree of the extension of residue fields. That's where the square is coming from. Okay, so this is telling us that this lambda I prime doesn't split completely. In this extension. But certainly, if we don't have, if a prime doesn't split completely on this step, it cannot possibly split completely all the way down. Okay, so certainly this implies that lambda I doesn't split completely. In L 1/p yk down to k. But now this is this implies this P indivisibility, local P indivisibility. Okay, so that gives us B. And now I have more than enough time to conclude with part C. Well, any questions about part B? Okay, so let's check part C finally. Okay. Okay, so part C, I recall. So now we fix the prime L1, the first one in the list, and now we want this class to be locally non-trivial at all the other primes. Okay, so we want this to be non-zero. That should be so for all I between 2 and t. Okay, so again, the way we're going to check this non-triviality is by checking that these primes, lambda I, don't split completely in a certain extension. Okay, and so here is the extension that we're going to work with. Okay, so we're going to take L prime over L to be the smallest Galois extension. Such that, okay, so we have this TL1 is some cocycle that with coefficients in the p torsion. Okay, so again, if we restrict to this L where we trivialize the p torsion, it just becomes a homomorphism from the absolute Galois group. Okay, so this restriction to CL1 is going to be a hom from this group to the p torsion. And L prime is going to be just the smallest extension through which these factors. Okay, so okay. So we're going to need to know something about this Galois group. So that's the content of this little lemma. Which is actually quite easy to prove. Okay, so this Galois group, it's also going to be isomorphic to the p torsion. And moreover, the plus and minus eigenspaces are each one-dimensional. Plus and minus eigenspaces under complex conjugation. Okay, so let's quickly prove this. Okay, so by definition, this restriction is already giving us an injection. Okay, so this isomorphism will be the one drawn for from this restriction. Okay, so the restriction of CL1 is a homomorphism which is non-zero by our hypothesis that, well, from what we checked last time. Okay, we have just checked that y sub k is in particular locally p indivisible at lambda 1. And we saw yesterday, and still here, I think. Yeah, here it is, that this local p indivisibility amounts to this non-vanishing. So in particular, the class CL is non-zero. Okay, and this restriction is an isomorphism, so it will remain non-zero after restriction. Okay, so this is non-zero and Galois equivariant. Okay, but G is the Galois group of Q adjoining all the P coordinates. And so this certainly acts transitively on the P torsion. And therefore, this is actually going to be surjective. Okay, so hence surjective. Okay, so that gives us that. And the second claim. So okay, and the second claim is just a consequence of the fact that CL1 is a tau eigenvector, as we already saw. Okay, it follows from this, together with the fact that the EP is irreducible as a G module. It's a calligraphic G module. Okay, so the same argument that we saw that we saw here. In the proof of this. In the proof of this lemma. Okay. All right, so now we really have it. Okay, so finally, okay, so we have checked in part B that in particular y sub k is locally p indivisible at this lambda 1. Okay, and this by the provision 5 from last time. Okay, so this is checked in B. Or by B, I should say. Okay, so this we know already. And this implies that partial lambda 1 of CL1 is non-zero. I just recall, I went back to the result showing this. Okay, but now this implies that, well, in particular, CL1 is, it has a non-trivial residue. So that means that it's not in the finite part, so it's not a Selmer class. It's not here. Okay, so now this implies that we have introduced before that extension M, which is the smallest one, trivializing the Selmer group. And now this class is not in Selmer. So if I take L prime and intersect it with M, I just get L. Okay. And that's going to be crucial now, because what we will have to do in order to check C is to actually, the lambda 2 through lambda t that we chose before, we need to be able to ensure that at the same time they satisfy another condition relative to this second extension L prime. And we will be able to impose both things simultaneously thanks to this relation. Okay, so this implies that without loss of generality, we may assume that the above lambda 2, so lambda 1 has been fixed, that one we don't ask anything further, but this lambda 2 through lambda t are such that on the one hand we have the same condition as before. This is conjugate to tau hi in here. Okay, so as before with tau hi square in here. Okay, so this is just as before. But also this condition relative to this new extension L prime. Okay, so this is as elements in this Galois group, L prime over Q, with now this tau H prime are, so that this is an element, a non-identity element in L prime over L, the plus part of this Galois group, which we have just shown is one-dimensional, so we can certainly pick a non-zero element there. Okay, and so we just saw that this is isomorphic to FP. Okay, and the reason why we can arrange both things simultaneously is because, well, the only thing that these things are in common is, so this element H prime and H, they fixed L, so we just need to check that they agree on the overlaps. Okay, and thanks to this condition, we can impose both things simultaneously. Okay, but so now we are really done, because we immediately check that with these choices, the prime lambda I, it's not going to split completely. In this extension, L prime. Okay, that's for all I between 2 and T. Okay, so indeed, this is because, okay, so we can quickly compute again the Frobenius of this prime. And that's going to be, again, these primes are inert, so we get the square of this guy, which is conjugate to this tau hi prime square, which we have chosen to be non-trivial. Okay, but this lambda I is not splitting completely in L prime, since L prime has been chosen to be this smallest extension, trivializing this class, or splitting this class. This implies that CL1 lambda I is non-zero for all I from 2 to 2. Okay, so now we have it. This gives us Kolyvaghin's theorem A. Okay, and with this, I'm done. So, yeah, thank you.
So, any questions?
Okay, maybe if there's no one else, can I ask a question?
Yeah.
Okay, I had a vague question about Euler systems, actually. This is Mahesh, by the way, Francesc.
Hi, Mahesh.
So, like, is there a formalism where you can use Euler system machinery to like in rank bigger than 1? So when the Selmer rank is bigger than 1 or something like that. Like, can you produce classes which are linearly independent? Is there a formalism of, like, how would you say that something? I mean, how would you like characterize this on the side of Euler system so that you produce classes which are linearly independent?
Yeah, so I think somehow the standard theory of Euler systems. So in the cyclotomic setting, as we saw in as Chanko explained yesterday, the theory that one finds in the standard references would tell you that if you have a non-trivial order system, then you can bound the strict Selmer group.
Yeah.
So you get a finite module, and then the one that you are interested in can be at most, for example, in the cases of elliptic curves, can be at most have at most rank 1.
Yeah.
Now, in the case of anticyclotomic type of order systems, like here in Heegner points, the situation is slightly different, but again, the conclusion is a rank 1 statement. So I think for higher ranks, there is no such statement like taking as input an order system and deducing of higher rank and deducing as a consequence that the Selmer rank is R for some R bigger than 1.
Right. The machinery seems very delicate, and I don't know how to characterize this on the side of Euler system, like,
Yeah.
How to set up the formula. Okay, thanks.
Yeah. I saw a question in the chat.
Yeah, two, 3 questions, I think.
Oh, so where do you start?
Okay.
Okay, so Timo, there's an article by Kato in which he develops an abstract theory for a system over Q. Is there something similar for anticyclotomic order systems? I think for anticyclotomic order systems, so in Rubin's book, there is a chapter towards the end where he sketches how his theory, his results, the results that he proves in his book, could be adapted to handle some anticyclotomic situations. But he only gives a sketch, and yeah, he says that it would require some work, but he indicates some directions. But more recently, there is ongoing work of Dimitar Yetchev, Jan Nekovar, and Chris Skinner, where they develop a general machinery of all the systems in the anticyclotomic setting, and so yeah, soon there should be available a general theory that encompasses these anticyclotomic Euler systems.
There's one more question. Which,
yeah. So the next one, I see. Are there generalization of Heegner points for any number field over K? Not that I'm aware of. Yeah, I think more generally, yeah, I think so. I guess so. Say restricted to the context of elliptic curves. So for abelian extensions of the rationals, we have Kato's Euler system, and for ring class field extensions of K, we have Heegner points. Now, for ring class field extensions of real quadratic fields, there is a conjectural theory of these star Heegner points or Darmon points that should provide an analog for real quadratic fields. And this has been generalized still conjecturally to totally real fields. And maybe nowadays there is even a generalization of this framework of star Heegner point to much more general number fields. I think yeah, there are some recent works by maybe Chevy Guitar, Marmasdeu, Santi Molina, who have developed this framework of introduced originally by Darmon for real quadratic fields to much more general context. But I think beyond Heegner points and Kato classes, everything remains quite conjectural. And maybe I could add also there is this theory of eclectic homology of Nekovar and Scholl that should also it's quite intriguing and might eventually lead to further progress in this problem. Okay, so there's another question by Timo. There is an article by Kato in which he develops an abstract theory of cyclotomic order systems over Q using étale homology to keep track of unramifiedness. Is there something similar for anticyclotomic? Yeah, I think. Oh, okay, it's only one question. Okay, so
yeah, it's the same question. I think it's just rephrased it with more
and
clarity.
And then what extensions are you referring to? Well, I don't know when this was asked, but yeah, I don't know what this question is referring to.
Maybe I can unmute Subrajit and then he can just ask over the mic. Yeah, Suprajit, I think you can ask in the mic. I'm just
Yeah, I think apart from abelian extensions for Heegner, yeah, I don't think. Yeah, usually, yeah, in the current theory of Euler systems, one always deals with abelian extensions of the ground field. I don't think anything has been any such thing as a non-abelian Euler system has been developed yet. But one has classes over non-abelian extensions and try to use them to bound some rules.
Yeah, so just sort of following up with the question, I have a question. So if you sort of start with a totally real field, let's say elliptic curve over a totally real field, then you have gross points, which is sort of similar to Heegner points. I think you also have the full Euler system when you look at, you take a CM extension. Points. Yeah, you take a CM extension of the totally real field, and then you sort of build an Euler system of gross points over that. Is that true? So I was thinking if you know any sort of analog of Heegner cycles in the totally real setting for the higher weight case.
In the Hilbert setting.
Yeah, in the Hilbert modular form setting.
Yes. So something like a counterpart of these Stark-Heegner cycles, but over totally real.
No. So what I'm saying is you start with a Hilbert modular form, let's say even parallel weight. Then you take a sort of a CM extension of this totally real field. Then do you have the Heegner, the analog of Heegner cycles?
Oh yeah, I see. Probably, if then maybe, but then in this case, as you probably know, the Hilbert modular variety doesn't give you the right Galois representation. You need to work
exactly.
on a Shimura curve on a unity Shimura curve, and I think for that you can use the give a similar construction as the classical Heegner cycles, but over this unitary Shimura curve.
Yeah,
working on a Kugasar over them.
Has it been, I think that written down anywhere? That's what.
Probably it can be at least, maybe it's at least, it could be appearing in Liu Zhangzhang, where they prove this very general VDP formula.
Right.
At least in some versions of their paper, they had some, essentially like such construction.
Okay, so there's one more question in the chat box.
Is there something like another system for GSP4? Yeah. So I think so in this case, one needs to distinguish between the spin and the standard, and for the spinel function, there's been an Euler system constructed in recent work of David Leffler, Sarah Cerves, and Chris Skinner.
So any other questions? First appearance of Euler system was in Kolyvagin's paper on the redshift.
Well, I think the first appearance of the term Euler system, which was in that article, but I think the first appearance of an what we now call an Euler system was in a few years earlier in Kolyvagin's original work on modular elliptic curves.
Heegner
yeah, absolutely. Yes, so they do, and I briefly alluded to that in the first lecture. I mentioned that we have these breakthrough results from the 80s by Grosegui and Kolyvagin, but more recently, combined with developments like the VDP formula and progress on Iwasawa theory, Heegner points have again played a key role in further advances in the direction of BSC.
Okay, so any more questions? I think we can take one or two questions. All right, if not, let's thank Francesc for this wonderful course.